This introduction is dedicated to recalling some very important expressions that we derived in the course on general relativity. So we have to be able to deal with tensors, and not just tensors, also, for example, the Christoffel symbol, which is not a tensor, and I showed that in the course on general relativity. So this is the Christoffel symbol. And let me recall the expression. We have gamma, alpha, beta, gamma equal to 1/2, and then we have the inverse metric tensor G alpha delta dg delta beta. Here we have subscripts because this is the metric tensor. If we have superscripts, we have the inverse metric tensor dx gamma plus dg gamma delta, or delta gamma, because this tensor is symmetric. So we have, for example, we can write delta gamma here with respect to x beta minus dg beta gamma, and then we take the derivative with respect to x delta, just like this. So this is the expression for the Christoffel symbol. The metric tensor, as I said, is symmetric, so we have g alpha beta equal to g beta alpha. Then we have other important expressions that we derive. So I will not recall all of the expressions that I derived in the course on general relativity, because we will not use all of them, of course, but I will just recall the relations that we will be using here in this course, because we will apply these concepts to derive some very important applications of general relativity. So we have an invariant quantity, which is also the line element, ds squared. This is equal to dx alpha g alpha beta dx beta. So this is the invariant quantity in general relativity. We started to see this expression in special relativity when instead of g alpha beta there was the tensor eta mu nu, or eta alpha beta if you want, where this matrix, this could be thought of as a matrix like this: 1 minus 1 minus 1 minus 1, 0 0 0 0 0 0, and all zeros here off the diagonal, something like this. Okay, so this is the Lorentzian metric tensor, whereas g alpha beta can be more general. It can take into account curved space-time as well. Okay, but we will say something more on this. And then we also have something else. We also have some other very important quantity or tensor in this case, which is the Richie tensor or Richie curvature tensor. I can write down the expression R alpha beta is equal to, so by the way, alpha and beta are two indices that range from 0 to 3. Okay, so usually Greek letters are used to denote indices that range from 0 to 3, or anyway, you can also think of the indices as ranging from 1 to 4. So it depends on the conventions, but usually in general relativity, the index 0 is used for time, whereas the indices 1, 2, and 3 are used for space. But anyway, the expression for R alpha beta is the derivative of gamma, alpha beta lowercase gamma here, with respect to x gamma, minus d gamma, gamma alpha gamma, dx beta, plus gamma gamma alpha beta, gamma delta, minus gamma here, alpha delta times gamma delta beta gamma. And we also saw that if we go to a frame of reference, to a local frame of reference, where we can think of the metric as very close to the Lorentzian metric here, these expressions here are equal to 0. So it can, this Richie tensor can be simplified. It can only contain the first two terms, for example. because gamma goes to 0 when we go to a local frame. That's what we discussed. And it can also be easily shown that R alpha beta is equal to R beta alpha. So this is symmetric. But let's try to see why. So let's try to find out why. Okay, so this expression here is clearly symmetric because gamma alpha beta gamma is equal to gamma beta alpha gamma. Okay, so we will take this for granted. You can easily see that gamma is symmetric, but we also derived it in the course on general relativity. So we'll take this for granted. Then we can also see that this expression is also symmetric for the same reason. Okay, and we have to show that, for example, this one here is symmetric, which might be non-trivial. If you just take a look at it, it is not very easy to see why d gamma alpha gamma gamma dx beta is equal to, so we have to show that this is true, d gamma gamma beta gamma dx alpha. So this might be useful to see the steps. I mean, it might be useful to see the steps that lead to this equality here, to prove this equality here. So we want to prove this equality. How can we do that? Well, we have to use the expression for gamma. So let's consider d gamma gamma alpha gamma dx beta. This is equal to d dx beta. And then we substitute the expression for gamma alpha gamma gamma. We have 1/2 g gamma delta dg delta alpha, and we take the derivative with respect to gamma, plus dg delta gamma dx alpha minus dg alpha gamma dx delta, just like this. And now we can see that these two terms here, this one and this one and this one, will cancel when multiplied by g gamma delta, which is this quantity here, because those two expressions are symmetric with respect to gamma and delta. So I can also cancel these two terms here. Therefore, this will become equal to, we have the derivative with respect to beta, to x beta, of 1/2, which I can also factor out of this expression here. And then I have g gamma delta dg delta gamma dx alpha. Now, it is also quite easy to see that if we consider a frame of reference in which G is diagonal, or we can also think of a local frame, for example. But let's just think of a frame where G is diagonal. It can be made diagonal because G is symmetric. And it is easy to see that this is equal to 1/2 d over dx beta. And then we have 1/g, where G is the determinant of the matrix G alpha gamma or delta gamma here. It is the determinant of the metric tensor. And then we have the derivative of the determinant with respect to x alpha. This is an expression that I derived more rigorously in the course on general relativity. So I will not delve into the details here, okay, because I did that in another course. But this is not really important here. I just want to remind you of some properties that might be useful when dealing with tensors. So I'm just trying to refresh your memory. This is equal to 1/2 d over dx beta d over dx alpha of the logarithm of g, or I can also put minus g here. It is more appropriate to put minus g because the determinant of g is negative. So with a minus sign it will become positive and the logarithm will be real, of course. The logarithm of a positive quantity is well defined. And the derivative of logarithm of g or logarithm of minus g will give me the same thing if you think about it. And now you can see that here, so I can also rewrite it like this. So this is a second derivative, 1/2 second derivative with respect to alpha and with respect to respect to beta, or vice versa. You can also swap the order of these two derivatives of the logarithm of minus g. You can see here that this expression is symmetric with respect to the indices alpha beta. Therefore, this equality here holds. This one is true. Okay? And finally, we have to show that this product here is also symmetric with respect to the indices alpha and beta. Well, this is quite easy to do, but let's do it below. We have gamma, alpha, delta, lowercase gamma times gamma, beta, lowercase gamma, delta. But delta is a dummy index here because we are summing over delta. So we also have to remember that when we have a lowercase, sorry, when we have a superscript and a subscript, we have to sum over them. And here we also have gamma, which is another dummy index. So let me remind you that this expression means that we have to sum over the index gamma from 0 to 3, and we also have to sum over the index delta from 0 to 3 of the same expression here. So that was just a shorthand notation which was proposed by Einstein, and it is very useful because we can omit these two summation symbols. Therefore, we can change the name of these two indices. For example, I can call delta, I can call it gamma, and I can also call gamma with a different name. For example, I can call it delta. So this expression is also equal to gamma delta. Instead of lowercase gamma here, I will put delta. Alpha remains the same, but instead of this lowercase delta here, I will have to put gamma. And then here I will have gamma of, instead of delta, I will have gamma, beta, and instead of gamma here, I have delta. But this is also equal, so this is a product, so I can put this gamma before this other gamma here, so I can rewrite it as gamma of gamma beta delta times gamma delta alpha gamma. And now if you compare these two expressions, you can see that they are equal, but you can simply obtain, for example, this one by changing beta to alpha and alpha to beta. Okay, so you can see that it is symmetric with respect to the indices alpha and beta. So that's what we wanted to prove. And therefore, it means that indeed the Ricci tensor is symmetric. So R alpha beta is equal to R beta alpha. So this is just due to the properties of tensors. Okay. And then let me also remind you of the field equations. Einstein's field equations. Einstein's field equations. You have the Ricci tensor alpha beta minus 1/2 the Ricci scalar, which is defined by contracting the Ricci tensor. So the Ricci scalar is defined as R alpha beta times the inverse metric tensor alpha beta. So this is how it's defined. Then here we have g alpha beta equal to 8 pi g, which is the gravitational constant, divided by the speed of light to the fourth power, c to the fourth, times the tensor t alpha beta. And if you recall, this tensor was the energy momentum tensor. Okay, sometimes this relation can also be written with mixed indices. So for example, we can also rewrite it as r alpha beta with an upper index and a lower index, and this is just done by contracting with the metric tensor appropriately. So I will not do it rigorously, I will just write down the expression. Then we have minus 1/2 times r, and then when we have mixed indices, the metric tensor is equal to the delta, the Kronecker delta alpha beta, and then we have 8 pi g divided by c to the fourth times t alpha beta, like this. So this is an expression that we will use because we want to solve Einstein's field equations for some particular but very important cases. I've also said something about, so I've already said something about the Lorentz metric, era alpha beta. And let me also say something more for the metric g alpha beta in the case of a weak gravitational field. So in the case of a weak gravitational field, so let's say very far from a gravitational source, for example, very far from a mass that's producing gravity, this tensor can be written in this form. So the first entry, the 0, entry, is perturbed by a very small quantity, and we saw that, for example, in the derivation of the Newtonian equations. So we derived the Newtonian equations from the Einstein's field equations just by assuming that the metric tensor in the case of a weak gravitational field can be written in this form that I'm going to write down in a moment. So we have 1 plus some very small perturbation here in the first entry given by 2 phi divided by c squared, where phi is the Newtonian potential, and then we have 0, 0, 0, 0, 0, 0 here, minus 1, minus 1, minus 1, 0, 0, 0, 0, 0, 0, just like this. This is also quite useful, and we will have to use something like this. Okay, so this was just a brief summary, a short summary of the most important equations and properties of tensors that we derived in the course on general relativity, and we will continue from here.